Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on January 4th, 2026, just 2 days ago. It introduces the first video face swapping framework based on a diffusion transformer, achieving an identity similarity score of roughly 0.66 while effectively eliminating temporal flickering. The paper is titled DreamID-V, Bridging the Image to Video Gap for High-Fidelity Face Swapping via Diffusion Transformer. And, as we'll see later, the visual realism it achieves on the new benchmark is really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. On Hugging Face, the 1.3 billion parameter model weights are ready to download. You will also find Python code examples for single and multi-GPU inference to get started. To see this in action, Figure 1 showcases the model's performance across diverse scenarios, displaying the reference face on the left and the swapped video results below the originals. Notice the second row, where the model successfully applies a human identity to an animated character while preserving the cartoon style. Moving to the fourth row, we see robust handling of occlusions, as the face remains coherent even when a hand covers the mouth. Finally, the bottom row illustrates performance on small faces in a wide shot, retaining fidelity despite the distance. Figure 2 outlines SyncID Pipe, the data pipeline designed to solve the shortage of paired training examples. On the left, the system takes a source image and a target video to extract pose sequences. In the center, the identity-anchored video synthesizer uses this information to generate a new video that swaps the identity while keeping the original motion. Finally, the right side shows an enhanced background recomposition step, which polishes the output to ensure high-quality training data. Moving from data generation to the actual model architecture, Figure 3 presents the DreamID versus framework itself. It relies on a modality-aware conditioning mechanism that splits the input into 3 distinct streams to efficiently manage different video attributes. On the left, the spatiotemporal context module processes the target video and masks to preserve the background and lighting. Up top, the structural guidance module extracts pose landmarks, using a pose guider to control facial expressions and movement. Simultaneously, at the bottom, the identity information is injected via an ID encoder to ensure the new face matches the reference. Finally, on the far right, the identity coherence reinforcement learning component monitors the output to minimize flickering and maintain stability. Figure 4 presents a qualitative comparison against state-of-the-art methods like face adapter and Canon swap. The layout displays the source face on the left and target video frames in the top strip, with each subsequent row showing a different model's output. Take a look at the bottom left scenario, which involves heavy occlusion as a hand moves across the face. While competitors often struggle here, the last row shows that DreamID versus maintains the identity perfectly behind the obstruction, highlighting its robustness in complex dynamics. Following the visual comparisons, Table 2 presents the results of a user study, where volunteers rated the generated videos on a scale from 1 to 5. The columns display average scores for identity similarity, attribute preservation, and video quality. As shown in the highlighted bottom row, the proposed method achieves the highest performance across all 3 dimensions. It scores 3.85 on identity similarity, edging out the image-based DreamID model, while also securing a dominant 4.15 in video quality. Complementing the user ratings, Table 1 details quantitative benchmarks across identity consistency, attribute preservation, and video quality. In the identity consistency section, the model hits an ID arc score of 0.659, clearly surpassing the previous best, DreamID. Crucially, the variance column shows a low of 0.0029, mathematically confirming the reduction in flickering. To the right, the attribute preservation metrics show the method also maintains high fidelity in pose and expression, balancing stable identity with realistic motion. Wrapping up, 2 takeaways stand out. DreamID versus successfully bridges the gap between image and video fidelity by deploying a diffusion transformer. Furthermore, the introduction of identity coherence reinforcement learning practically eliminates flickering, suggesting a robust path forward for consistent video editing. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.